Hello and welcome back to Chapter 1. Today we're going over section 1.7, transformation of functions. And our objectives of this section is to use vertical and horizontal shifts, reflections, and non-rigid transformations to sketch graphs of functions. So let's get into it. Remember last time we talked about parent functions, so we're going to be using quite a bit of those. So the first thing we're going to do is show graphs. Okay. So a lot of functions are actually transformations of other functions. So let's say, for instance, you have here h of x is equal to h squared plus 2. If we know that f of x is equal to x squared, right, everything here, this h of x consists of all the values of x squared, but add 2 to them. So what does that mean? That means that the value of x is exactly like f of x, except we increase it by 2. But what does h of x represent? Well, that represents the y values. So this is a vertical shift twice, right? So it shifts up 2 units. So if you see the parent function and you add anything to it, it gives you an upward shift. So let's say here, so basically you're saying here's the function and shifting it up 2 units. Now, if you were to do a negative, like basically an x minus 2 in here, this 2 inside the parenthesis where you have that inside the function, that shifts the graph to the right 2 units, okay? And you can go ahead and plug in values and check to see if I'm right, but I am right. Okay, so here, this g of x, which is x minus 2 squared, is basically f of x minus 2, which is a right shift. So here are the, here's basically in general, we have, if you have a graph y equal f of x, a function, a vertical shift is when they just add a number to it outside, number by itself, a constant. And a shift down would be when we subtract by a constant. And we shift to the right when you have, you replace the argument with x minus c. And we shift to the left when you have x plus c. F of x plus c when you insert that. Okay, so another way you can think of it is some graphs can be, you basically, if you understand this concept of shifting, it's very easy, and you memorize the parent functions and their properties, then it's very easy to start being able to graph a lot of functions, because we know that you can have vertical and horizontal shifts. So remember, verticals are outside and horizontals are on the inside. So if it's number x minus a number, it's to the right, and if it's plus, it's to left. This is something I used to use a long time ago, like 12 years ago, and this was really helpful to people. So right, and so if you think about that, you basically can generate a family of functions where you have the same shape but just different locations in the plane, like they've just been shifted. So let's look at this example. So let's say A, you have x cubed minus 1, yeah? So here's x cubed, and that minus 1, all that did was just bring it down 1 space. So everything here has been brought down 1 space, okay? So that's it. It's just a downward shift. If you have here x plus 2 quantities cubed plus 1, it's still the cubic function. However, you have a left shift of 2 and an upward shift of 1. So starting from here, you would go over 2, up 1, and then draw exactly the same graph. Okay. So that's the same thing if you do, it doesn't matter the order that you do it. You could have done the vertical shift first and then the horizontal shift. It really doesn't matter. Okay, now let's talk about reflection graphs. So a very common type of transformation is a reflection. And so basically it's kind of like you imagine an axis or a line to be a mirror, and you just draw its reflection. It looks exactly the same except flipped over, yeah? So if you consider the x-axis to be a mirror, let's say you have x squared, Negative x squared will be the mirror image, basically takes all these positive y values and turns them into negative y values. And so it's exactly the same graph, but just facing down, okay? So positive people smile, negative people frown or be sad. So there it is, the frown face. Okay, so in general, you have a reflection across the x-axis if the negative is in front of the function, and you have a reflection across the y-axis, right? The y-axis becomes the mirror if the negative is inside the function. So if it's f of negative x. Okay, so let's see here. This is the graph of f of x is equal to x to the power 4, yeah? Now, here are different transformations. Let's see if we can write an equation for each of these. So this is x to the 4, something happened to it, and then here something else happened to it. So you can see that there is a negative, there's going to be a negative in front of it because they're both facing downward, right? And then this one looks like it moved up twice, and this one actually looks like it moved over a couple of spaces. So let's look at this. So you have here, it's negative x to the power 4, yeah? And it's moved up, so it's a vertical shift of 2, so you go up 2 and that's it. If you take the graph, you move it over 3 spaces to the right, so that's x minus 3, it was moved over, and then it's flipped across the x-axis, so there's a negative in front of this. Notice that this is in front of the parentheses, yeah? And this is a horizontal shift because it's inside the parentheses. Okay, so when you sketch the graphs involving square roots, we have to remember to restrict the domain to exclude negative numbers inside the radical. So for instance, like say we have here, what's the domain of g of x when the function is negative square root of x? Well, still, anything underneath the radical has to be greater than or equal to 0, so that's that one. What's the domain of h of x when there's a negative x underneath the square root? Well, in this case, x has to consist of all the non-positives, right? Or the negative numbers including 0. So because a negative times a negative will make it positive, therefore making it okay to square root. Okay, and then finally here, x plus 2 itself has to be greater than or equal to 0. So if you solve for x, that inequality for x, you see that x has to be greater than or equal to negative 2. This negative outside does nothing, like who cares? We just care about what's underneath the radical. Okay, so let's continue to non-rigid transformations. So non-rigid transformations, so first rigid transformations are horizontal shifts, vertical shifts, and reflections. Why would they be called rigid transformations? Because the shape of the graph itself has not been changed. Okay, so the shape is the same. It's just either been moved around, it's been shifted, or reflected. Okay, they just changed the position of the graph. Now, non-rigid transformations actually kind of distort the graph a little bit. They change the shape of the original graph. So let's say, for instance, you have so a non-rigid transformation can be represented by f of x multiplied by c. So g of x could equal a constant times the function, where if the constant is greater than 1, it's a vertical stretch, and it's a shrink if you have a fraction between 0 and 1. So that's if you multiply the entire function by a constant. So what if you have an input where you just multiply the x, not the f of x, but the x? So another one would be like h of x is equal to f of cx. So now the constant is inside. You basically multiply the input variable by c, right? So then the transformation will be a shrink when it's greater than 1, and a stretch when you have a horizontal shrink, and a horizontal stretch when c is between 0 and 1. So let's do some super fun examples. Here is my absolute value of x function. What if I multiply this by 3? Okay, so what's going to happen here? Think about this. So here you have the point 1, 1. If you multiply by 3, it's going to jump up to 1, 3. The y value will jump to 3 and so on. So basically it's a stretch of 3. Each y value is multiplied by 3. So also here you have 1/3. Let's say 1/3. This is the regular f of x. Now your graph becomes more fat, right? Like fraction equals fat. It grows more slowly. This is because the y value is multiplied by 1/3. So it grows 1/3 as fast as the original one does. Okay. So let's do some super fun homework examples. So let's see here, we'll do one. So you're given this set of points, and then you want to go ahead and draw the graph. Okay, so the first one is f of x plus 2. Well, that's easy. You just take each point, and you add 2 to the y values. So 0, -1 becomes 0, 1. 1, 0 becomes 1, 2. 3, 1 becomes 3, 3. And then 4, 2 becomes 4, 4. So notice I added 2 to the y value. Okay, so then B, you're inserting -2. So what that means is it's a horizontal shift to the right. So you take each point, so starting at 0, -1, and you shift it over 2 spaces, boom, okay? So the other one would be 1, 0, shifted over 2 spaces, there it is, okay? The next one was 3, 1, shifted over 2 spaces, here it is, and then 4, 2, 4, 2 is over here, and then shifted over 2 spaces, and you get 6, 2. Okay, then for C, you're multiplying everything by 2, right? So it's growing twice as fast. So you're multiplying y by 2. So here, 0, -1 becomes 0, -2. 0 times 2 is still 0, so this point stays 1, 0. 3, -1 becomes 3, 2. And then 4, 2 becomes 4, 4. So that's a stretch. You see how it stretches vertically. Okay. And then D, it's just reflected across the x-axis. So basically, this point comes up here. This point down here moved up to here. This point stayed where it was. This point 3, 1 went down here. And this point 4, 2 went down to 4, -2. And then E was shift over to the left. So you notice it just goes to the left 3 spaces. 1, 2, 3, here it is. From here, 1, 2, 3, here it is. From 3, 1, it became 0, 1. And then from 4, 2, it moved 3 spaces to the left. So each point was 3 spaces to the left. And then F was a reflection across the y-axis. So notice how the original was this way. And then it's basically, this one was on the y-axis, so it stayed. This is the opposite of 1, 0, -1, 0. So the next point was 3, 1, so it became -3, 1. And then 4, 2 becomes -4, 2 because it's the opposite across the y-axis. And then finally, the horizontal, there's like a stretch here because you have here 1/2 of x. So what that means is that you'll get to the same points, but in half as much time. So x is half as much as it would normally be, right? So 0 and -1 is the same, right? But in order to get to 1, 0, to get to a y value of 0, it takes you twice as long. So x grows by 2. Then 3, 1, the x grows by 2, so it's a 6, 1. And then 4, 2, the x grows by 2, and that's 8, 2. So basically, it takes twice as long to reach the same one. So it grows half as fast in the horizontal direction. Okay, so 33 from the homework. Let's say we need to identify the parent function. Obviously, this is going to be absolute value of x, right? Because here's the absolute values. B, describe the sequence from F to G. So if you have absolute value of x, we're going to move it to the left 4, right? It's going to be reflected across the x-axis because of the negative. And then we're going to move it up 8 units. So there it is. It's right here. So you have f of x. You have f of x would be like this, right? Then you flip it across, you move it over 4 spaces, and you move it up 8. Here it is, and it just is facing downwards. Okay, and then this one is identify the parent function transformation and write an equation. This looks like the square root of x, right? But it's reflected across the y-axis, so it's square root of negative x. And additionally, it's growing. It looks like it's taking twice as long to grow, right? So it's half square root of negative x. So it's half as long. So in order for it to get to 1, right, this would have to become square root of 2, right? So then right here. So yeah. So that is that one, and then that's all I have for you. Your super fun homework is 1 through 65, every other odd, and I will see you in the next video.